Let's give him a hand and good luck, Mouad.
Thank you. Hi, everybody. Sorry. So, hi, everybody. I'm very glad to be here today to share with you all the findings that we came across with my team when we started analyzing the HID two-factor application. Yeah, so I think now it's 3 months ago that we decided to go for this security analysis. So yeah, I'm particularly excited to show you today all the interesting stuff that are implemented inside this type of application. So for that, I'm going to follow this agenda. There is mainly 4 parts. The 3 first one are here just to lay the ground for the last one, because the interesting, as you can guess here, the interesting points are in the last one. So before that, I hope to present you some key points that will help you to understand all the overview of the analysis. So the first part consists mainly in introducing the application, how does it work, what is the infrastructure that is generally used to implement this kind of application. Then I'll move to the overall methodology that I followed all over the analysis to gather the information for this analysis. And I think this is also an interesting one. I will just show you all the security mechanisms that were deployed by the application to protect yourself. It's very interesting here to see how this kind of application are protecting, let's say, their intellectual property. Oh, the first part, I think everybody here is very familiar with the hardware token. So I guess that at least one of you are using this kind of application. So here you have a hardware token that an end user is using to generate a one-time password. So this is embedded in a hardware device. So yeah, we can till now understand how things are implemented behind the scene. But yeah, the user here just getting a one-time password and send it with its login and password to the VPN gateway or whatever you want, something that will authenticate you against a remote infrastructure. And the idea there is to have an access to your internet network. So now take the hardware part and replace it with a software part. For our case, we are talking about HID logo that you can see here each time. So the end user here is going to use a mobile phone as a device to authenticate himself against an authentication gateway. So the application will be installed on a mobile device. Here, HID can be installed on different flavors as Windows Phone, BlackBerry, iPhone, and Android OS. Again, here, the end user just grab a one-time password from the application. So the HID pop-ups an information here that you can see, and the end user can get the one-time password and send it again with his login and the password to the VPN gateway, as I show here. So for our study, as I previously showed here, there is many flavor of the application. For our study, we decide to focus only on the Android one. But I am telling you also that we decided after to go for the other operating system just to compare the result that we obtained during our analysis regarding the Android version. And as you know, the Android market is the only market that offers the possibility to get rapidly and efficiently an application package as the opposite of the other stores. If you one day decided to go for a Microsoft store to grab an application, it's not that easy as you can think. Yeah, so we decided to go for the Android version. The main risk that we wanted to assess here was to check if an attacker who has the ability to go and steal the device to assess the risk if the attacker is able then to store all the configuration files that belong to the application and replay them without having any secrets. So that was the major risk that we wanted to assess. And consequently, we wanted also to know how the application protects itself against all reverse engineering mechanisms, how the application identifies itself that it is running under rooted devices and so on. So that is our main objectives. But before that, all I want to show you now is just a brief overview on how the application is used on a daily basis, on real life. So once the user grabs the application, install it on its mobile device, in our case, Android one, he has to start it for the first time. The application should talk with a second part. The second part here is the Smart Token Management Portal. So this component comes into play to ensure the enrollment process. So the user, for the first time, get a serial number that the application generates for the during the first execution. The user, as you can guess here, manually has to achieve all the enrollment process. So he takes the serial number and send it to the management portal. The management portal then generates an activation code, and the user again get this activation code and submit it to the application. And finally, the user get a registration code that he has to send to the final application to terminate all the enrollment process. As you can see here, there is no internet or network connection between the two components. All the stuff is carried out manually. So when we started our analysis, the first thing that we started digging in it was studying let's say, the security mechanism that the vendor itself promotes during in its communication documents. And here is some security means that normally are deployed and implemented into the application. But for us, what is the most interesting is the first one. So it appears that the application has several mechanisms against reverse engineering. So they deployed all obfuscation techniques and symbol stripping to remove all the information that an attacker grab during its analysis. So when we see something like this, we prepare ourselves psychologically to deal with this kind of application. And the second point that I want to underline here is other means. So normally the application should not work under a jailbroken or a rooted device. So that's the first observation. Unfortunately, when we started our analysis, the first step simply failed because the application ran normally under an Android emulator, for instance. We carry on our agenda. So here I just presenting the global methodology that I followed during the analysis. Nothing new here. So two main components, two main phases. I go back and forth between two main techniques, code analysis. So here I mainly used IDA Pro for reading the Java bytecode and for debugging the Java bytecode. But as you know, there is a plethora of tools that you can use for this kind of techniques. And the second technique is the behavioral analysis. So the idea here is just to run the application and grab all the logs and the information that the application can generate under an emulator, for instance here, and try to analyze all these logs. So the main result that we should mention here is that, firstly, the application creates two configuration files, the OTP token device and the OTP token status, and massively use crypto functions, especially EAS operations. This result was obtained by Droidbox, a dynamic analysis tools. So yeah. From here, when we came across this observation, we stopped and we told our customer that Yeah, indeed, there is a problem with this application because it uses always the same encryption key for its ES operations. And whatever the package we downloaded from the market store, we always found these keys. So we stopped here and yeah, we decided to go deeper and further into this analysis. So we opened the box, and the first thing we faced up was the security mechanism that was used by the application to protect itself. The first one, the first mechanism was the name obfuscation. So it's a simple mechanism, but it can be very, very hard for an analyst to deal with this kind of techniques. The idea is very simple here. We just replace all the meaningful information that can be embedded into an application by non-meaningful names, as you can see here, and why not using Unicode characters. So reading this kind of code, I can assure you that is very, very hard. Yeah, and the idea here is my main work consisted in translating these names into something that has a meaning inside it. So yeah, so I refactored all the code to have something like this. So that was the first mechanism. Then it comes the string obfuscation, a simple thing also here, nothing new. The application tried to protect itself by hiding all its strings. Actually, when we started looking for some special strings as those that are related to the application configuration file, as here the UTP token device, we didn't find them in the application, and yeah, we started guessing that there is a kind of mechanism of this kind of mechanism was really implemented by the application. At the opposite, when we started filtering all the strings that were embedded in the application, we came across some interesting ones. Those ones that are strings that reveal the use of some cryptographic functions. And by digging into the internet and by comparing the code, we found out that it was a bouncy cancel library that was used by the application, and that helped us to refactor a big part of the application. Yeah, to mitigate this kind of techniques, nothing new. Also here, just we spotted the function that was in charge to decrypt all the strings. We wrote an IDC script under IDA who grabs all the output of these scripts. So here, as you can see at your right, on your right, you can see all the strings that we were able to grab during a simple execution of the application. And here we were a little bit happy because we saw we saw new things that were interesting for us, especially the use of the standard Java API. So here we are sure that we can break somewhere to get more information. That was the second main. The third one was the Java reflection, another layer of obfuscation. This one, yeah, when you come across this one easily when you start reading the code. Each time you try to follow a call of a function, you just you have a wall in front of you because instead of using just a direct call, the application is using 3 calls to call one to achieve one application. And yeah, so the Java reflection techniques is just the property of a class to inspect itself and to have the ability to call a method or to modify an attribute of this class, but by inspecting itself. And generally, we use three APIs for name, get, method, and invoke APIs to implement this kind of techniques. So here are the mitigations. Yeah, no real mitigation, just using IDA Pro to spot this kind of techniques and deal and we live with that. And during the analysis, we spotted all the meaning of each function, and we rename all each function. And finally, yeah, the most interesting one was the class encryption mechanism. So the application actually embedded in itself two byte airways that corresponded to the real functional application. So when you start reading let's say the Android application, the code of the Android application, there is nothing interesting in that portion of code. But when you arrive at this level of mechanism, you start understanding the things that are behind the scene, because the application starts to decrypt a part of the application, and this part corresponds to the real functional application. That was the first point. The second point is, it generally use the same EUS encryption key and IV airway to decrypt and encrypt this airway. So whatever the package that you download from the market store, Android market store, you will always end with these two airways that correspond to the encryption keys used by ES for its decryption process. So for the mitigation, what we done here, just remember the result that I'm displaying here is the result of the string deobfuscation phase that came just before. When we read all the strings, the order is very important, because the order reflects the order of the application, the execution of the application. So we can easily spot the use of a cryptographic function, and then we can just break at the right moment, and especially here, the moment where the application will start to decrypt itself. So we can stop there and dump all the content from the memory. And here again, we come across with a Java byte, little bit obfuscated, but we can deobfuscate it easily and start reading the code. So at this level, we dealt with all the security mechanism, and we are able to start reading the code. Yeah, just reading the code, probably debuging it, and trying to understand how things works behind. So the end part is for me, is the most important one. So once we had the code, we asked ourselves, what are we looking for now? Really, we are looking for something like this, because the algorithm used for generating one-time password it's a standard algorithm. It's not something new. It's not something obscure. It's something known by everybody. So we just took the RFC here and tried to understand the content of the RFC, and draw this kind of schema to try to understand what are we looking for. So for our case, we are trying to find portion of code that implements this kind of algorithm. So what we have here, to understand the logic, we have various elements. The first one you remember the decrypted airway that contain the application functional code. And we have something that we got from the behavioral analysis. We know that the application use mainly two configuration files. So for us, the main entry point will be the two configuration files. So we are going to start from this file, trace back all the elements that deal with this file, all the mechanism and the functions that manipulate these files to find how the application works. The first step that we carried out was just to find how the application read and write to these files. And for that, we wrote a proof of concept. So we read the Java code, and we decided to write a proof of concept to understand how things works. And at the end, we had our proper parser of these two files. So here at the bottom, you have the first file, which is the OTP token device, and the second file, which is the OTP device status. Now I'm telling you that the most important one is the bottom one, and the second one is not such as important as the first one. And the methodology here is what I did really in real life. I took every parameter, every line. So I took the first one, the second one, and so on, and started tracing back each parameter and trying to understand how the application generates these parameters and how the application use these parameters when it reads the configuration file. So it was a really tough work, but here what I put in red is the result of my study. That correspond of the most important one. So we are going now to trace back all these red parameters to understand how the application works. So yeah, that was the kind of code that I had to deal with the first day, something unreadable. I don't know if someone here is able to read this kind of code. But after eliminating all the obfuscation mechanism, refactoring the code, we came to something like this. And this time, we can see that it's very easy to read the code and understand what is behind the scene. So from now, the main work was just reading the code and understand how things works. For us, the entry point, as I told you, was the OTP token device. So we took this file and we started analyzing each parameter. The third red parameter, you remember, was stored in this kind of file, and it seems that this parameter is the one-time password key, which is encrypted using a 3DS algorithm. So here we have the you have the one-time key that is submitted to 3DS, and the encrypted form is stored into this file. Yeah, so that's the first finding. Now we are going to trace back the one-time key to understand how this key is generated. So be careful here. Previously, I'm mentioning here that the key OTP is about 24 bytes. But in reality, the key is split into two main parts. One part corresponds to 20 bytes, and the second corresponds to 4 bytes. And the 4 bytes are generated using, firstly, I call this function getRandom because I just reading the code quickly, I thought that is something generating something random. But in real life, it was not such as random because it just took the current time in milliseconds and implement a SHA-1 on this seed and extract 4 bytes from this result. So here, if you can say yes, this function is kind of deterministic. If you have the same current time millisecond each time, we can get each time the same 4 bytes. Just make this information here, and we will come back to that. So I carry on. Once we have these 4 bytes, the idea here is to see how the 20 bytes that we have at the beginning are generated. So the schema here shows you that the application is using PBKDF2 to generate this 20 bytes using the activation code. And remember, the activation code is something that is generated by the server, and it's also using the salt, which is derived from the serial number. So also here, the function that generates the salt is the deterministic function that take the serial number and generates the same value each time. Okay. Now, so we saw the key OTP part. What is interesting to see now, the key I part here, so the key that is used by the application to encrypt the key OTP key. The application usually again the PBKDF2 algorithm for that, and this time the application uses a master key, what I am calling here a master key, and we are going a little bit further to see how this master key is generated. Master key, again, the serial number submitted to the deterministic functions to get the key I for the encryption task. So here we can start to ask ourselves, where is the pin? Because as I told you at the beginning, when the user ends its enrollment process, he should protect all the information using a pin. So where is the pin in all this stuff? So yeah, the pin is used here to generate the master key. So the pin that can be a digit between 4 and 12 digits is submitted to SHA-256 and then encoded with base 64. The same process is done on the Android ID, and as you know, the Android ID is a security attribute used by Android devices to uniquely identify an Android device. And I think that the idea here was to use something that is very specific to each device. But as you know, the Android ID can be modified on an emulator or on a device as you like. So we do the same thing on the Android ID, and we concatenate the both element, and we get the master key. So the third vulnerability. Just having this in mind, we can state that an attacker can clone and enroll HID soft token application. So he had to copy the HID configuration files, the OTP token device and the OTP token status. And for that, he need a root access on the device. So at this level, you can imagine all the scenario. The attacker has a physical access to the device. He stole the device, he root the device, remotely access the device using a known exploit as you like. But the idea here is just to get an access to the configuration file and get them. He has also to get the Android ID for the victim device. If the attacker has both of this information, he can clone the application and use it. But the problem is the attacker has to have a valid PIN to have a valid one-time password. But because the trick here is that the application generates a value, a one-time value, whatever the PIN is submitted to the application. So as you can guess here, if the attacker go for a social engineering scenario or try to install a keylogger on the device or something like this, the idea is just to get the PIN. If the attacker had the valid PIN and satisfies the two prerequisites that I've just underlined here, he can clone the application. So we did the test, and actually the test was okay because we had a valid access to the test platform that we were using. Okay, so that was the first vulnerability. But the question, as you know, as a researcher, we have always questions. If there is another way to get the PIN. So come back to the schema that summarizes how the master key is generated, but this time, instead of using the master key as an end result, we are using a variable that I'm calling here just something grabbish to illustrate the meaning of the variable. And this variable is used in the code, and effectively, what's happening, it's when I was reading the code, I came across this portion of code. I was very happy because the application indeed stores the PIN in its configuration file using a SHA-256 algorithm, and it was okay. I was very happy, but few lines after, I identified that the application, this code branch is never executed because the application is testing a kind of a flag variable, and this flag is always set to false, and this branch code is never executed. So I suspect that there was a time where the PIN of the application was stored in SHA-256 in the configuration file. Okay, so here again, fail. So after a cup of coffee or more, with my team, we decided to go and reanalyze all the stuff to spot if there is something interesting to grab the PIN code of the application. Because for us, it's very class if we can get the PIN code from the application itself without going for a social engineering scenario or something like this. Remember? I put everything in one slide to have a big overview of the internal functionalities of the application. Here you find also the OTP token device, the encrypted key OTP used to generate the one-time password. Here we also spot the key OTP split in two parts, the 20 bytes and the 4 bytes. Okay, so here we draw all the stuff in a in a whiteboard, and we started to think what we can do here to get the pin. In fact, the OTP key is 24 bytes. The 20 bytes are generated using PBKDF2 algorithm, but the 4 bytes that comes at the end of the key OTP are generated using SHA-1 algorithm seeded by the system get current time millisecond. So the idea here, if I get the value that was used to generate the SHA-1 value here, if I get the return value of this function, I have the 4 bytes. And the problem now, from where can I get this value? Because if you take this schema, if I have the correct value of the current time in a millisecond, I can generate a 4 byte here. If I have the 4 byte here, I can do a kind of brute force because the pin, I don't know the pin, but I'm looking for the pin, so I can brute force here the pin by insert it at this part. The Android ID value, I know this value, so I can redo all this mechanism to have to decrypt the key, but I need somewhere a stop condition for me to stop the brute force. So when I decrypt the triplet death encrypted value, I need something to tell me you are on the right way, you have the right key. So the stop condition here is these 4 bytes. So if I got the 4 byte, the valid 4 bytes, I have my stop condition. If I have my stop condition, I have my valid pin. But the problem here is what was the value that was used by the application to generate these 4 bytes? And guess what? In the configuration file, the application stores 2 values, 2 timestamps, the beginning of the enrollment process and the end of the enrollment process. So if I have these 2 values, I can guess where this operation has been carried out between this range of time values. So I have the time values. I can now brute force all the 4 bytes that are possible because I have the beginning and the end of the process. I can generate all the 4 bytes. If I have all these 4 bytes, I can go then for the other side to a brute force attack, submitting all the pins that I want to find, and I have my stop condition. You can guess here that we have some collisions, and for that, in consequence, we are going to have a number of candidate pin. And yeah, I will show you after how we can choose the right one. But yeah, that was the attack that we can trigger to get the pin. So yeah, as I said before, this was our stop condition to trigger a brute force attack and get the pin. So here I am showing you the proof of concept that we developed in intern to demonstrate this attack. So this proof of concept just took as parameter the configuration file, and based on the content of this configuration file, he tried to do the brute force. And as you see here, there is a lot of candidates, but what we did is just to try to do a statistical analysis to see which one is the most possible one regarding the execution of the operation during the time. So to conclude, that was an interesting study in terms of technical challenge and results. As you can see, an attacker now is able to steal the configuration file and retrieve the pin without going for a social engineering or stealing the pin. The study took 1 month workload, I think. The vulnerability has been reported to the vendor on July the 19th. The vendor was very responsive and currently is working on a patch for this version of the application, and at the same time is working for a new design of the application. Questions? Yeah, I understand the question. So the idea here is was other place that we can get the timestamps. Yeah. So uh, in our real life, what we did before coming to this finding, so we decided to go for the file configuration creation timestamp. So the first idea was that. So we needed a timestamp, so we just went for the timestamp of the creation of the configuration file, and from there we started our brute force. But with having some time to reanalyze all the stuff, we spotted these two values. So if we didn't have these two values, I think that we were able to use the creation file timestamp.
Did that answer your question? Okay. Any further questions? All right. Well, then I think we should say thank you to Mouad. Thank you.
Thank you.